Now, just now we talked before the break. We stopped at here. So there is a list of alloy here that are exposed to different temperature, and their penetration was measured on this table, right? Now we talk about sulfidation. Sulfidation means the word itself, you know that it linked to sulfur S, right? So we already done oxidation. Now we look at sulfidation. Yeah. So sulfidation, it linked to sulfur S. It is the condition of what will happen is something like if you on a blade itself, for example, this photo, it tell you that it's you see the discoloration, the color changing on that, and what else? So this is the microscopic observation. So you see there's a hole over here, and there's layer of oxide on the surface. Okay, but anyway, when we talk about sulfidation, is linked up with sulfur compound. Yeah, it link up with sulfur compound. What else? And you can see from this statement here, sulfidation always at the front of the observation, which is here, compared to others lah. They here got oxidation layer, but sulfur content will always appear at the front if the environment you have a sulfur element there. Okay, all right. A researcher called Lai, in his publication here, Lai something, high temperature corrosion, high temperature corrosion issues in alloy selection, published in the Journals of Materials, volume 43, page 11, volume 11, volume 43, page 54 to 60, published in 1991. Okay, quite an old publication, but it gives you some insight on sulfidation. Sulfidation, according to Lai, in his research, right, on high temperature corrosion, you have three categories. Yeah? You have three categories. So first one is hydrogen sulfate mixture. Second one is moderate reducing the mixed gas environment. The third one is sulfur oxide containing atmosphere. So you have three categories. And we're focusing on gaseous environment. Okay, so for sulfidation, we look at operation that are exposed to sulfur or gaseous environment. First, hydrogen sulfate mixture. Second one is the mixing of other gases. The third one is sulfur oxide atmosphere. Okay, so there are third category of environment here. Hydrogen sulfide, other mixture, hydrogen, water, carbon dioxide, and so on. And another one is under sulfur oxide atmosphere. So under to line, you have three. Yeah? You have three category related to sulfidation. Next, we look at standard steels. So standard steels that exposed to sulfidation corrosion, normally they will go into a treatment. The equipment and the standard steel equipment, they'll go through a treatment by using 2% soda acids solution or ammonia solution. They will dip, or not dip, but they will expose the treatment. We call it treatment. You send the metals into the oven or the treatment process unit. They will spray they will spray ammonia or 2% of soda acids on the subject itself. Okay, So the intention is to reduce the formation of acid. Okay, so for standard steels, they have one treatment for sulfidation. This is one of the example in the industry. So for standard steel, they will use ammonia or soda acids. Why they use ammonia or soda acids is to avoid formation of acid. Okay, and you know corrosion, when you have acid, it will going to accelerate the corrosion rate. Yeah. So again, this is the main thing when you talk about sulfidation. Acid is not a good thing. So these are the explanation what happens if you have acid. So when you have acid, you have intergranular corrosion and stress cracking. Another one is again you see chromium and MO, chromium and MO alloy. This is the solution, the solution for sulfidation corrosion. They will use chromium and MO to prevent or not to slow down the corrosion. Okay. So this is a sample of chromium MO alloy. It looked like normal steel, but you have to go inside the material to see the content. Yeah? But this is what the outlook of the material. Sometimes this material, we call it chrome moly. Okay, chrome moly. Chromium molybdenum, right? CRMO alloy. So this is one of the example how we control sulfidation corrosion under high temperature corrosion problems. Okay, so this one an example how you handle sulfidation. Yeah? So this one you can read. Okay, chart again. All right. So what does this chart tell you? This is a test works on authentic steels under two axes. One is hydrogen concentration and temperature. So x-axis is temperature. This is hydrogen sulfate. This is a hydrogen sulfate percentage. So you increase the hydrogen sulfate percentage and you increase the temperature. Right? You will see this is the corrosion rates. Okay, so you give you the lines constant. You have all this value. Right, you have all this value. So for example, the first one is very, very small on your screen. First one is 0.51. The last one is 0.0025. So this is the extreme case. This is the lowest value you can get. Okay, so meaning what does all this number means? Is in the unit of inch mm over year per year. So the higher the number would mean is corrode faster. The lowest means slower. Corrosion still happen, but slower compared to this line. This one is slow, this one is fast. If you compare these two lines, yeah. Okay. So this graph tell you what happens if you increase the temperature. For example, you follow this line. If you look at this line A here, you increase the temperature. At some point, the sulfate will go down. But if you increase the temperature, it will go up again, right? Yeah. However, from this graph, you get a constant value. It measured at 0.025 inch mm dot over year per year. Y exponential minus 1 is divided by the parameter here. It's a rate that you use to compare materials, right? Higher is not good, lower is better, right? Okay. Okay, so we try to look at temperature and the hydrogen sulfate concentration. Again, what is hydrogen sulfate? We need to recall back the chemicals properties. I can't find, there is chemicals, compounds, chemicals diagram for H2S, but as an engineer, you have to aware because later you might appoint as a safety officer in some of the construction projects or in some of the plant that you're going to work in. So hydrogen sulfate is something that very dangerous. It's a smellless gas, but it's very poisonous. All right. So normally when you work in the industry that exposed to generation of hydrogen sulfate, normally you'll see all these signs at the entrance. You need to wear protective gear, something like that, right? And sometimes the company, the safety officer or safety manager will assign one unit of these devices to measure the content percentage of hydrogen sulfate in that particular workspace. Normally it's a confined space. Normally it's when you are doing some tunnel, you do some tunnels, civil projects, or you go into exploration of site where you have the high chances of hydrogen sulfate. Then you need to carry all these PPE, personal protection equipment, for example, this gauge and this gauge, into that working space. Yeah. So this is a graph. On the x-axis is the percentage, not percentage, it's a concentration of your H2S, your hydrogen sulfate. If you increase the penetration, you measure. So for example, this one again, y equal to mx plus c. Your y is penetration, x is the concentration of your hydrogen sulfate. So this one has a positive gradient. If you increase concentration, penetration increase. Right? All this name you can zoom in later in my slides. But what is important, you manage to read the graph. Okay, manage to read the graph and you're able to compare lines to lines or material to material. Huh? So each line represents different material. Okay, meaning this line is the lowest compared to other element over here. It's the lowest, but corrosion still happen, penetration still happen. If you compare this one and this one, the gradient is different. This one is more flat, but the penetration a bit is higher. If you pick this line and this line is higher compared to this line. And one interesting line over here, you see a flat line over here, is called carbon steel. You see carbon steels, you have a straight line. Again, what I mean by straight line? It means the carbon steels, the penetration only happen. You see the line here is break over here and do not continue from here. The carbon steel data only have over here, right? You see these lines, flat line, you extend down. There's only certain level of concentration of hydrogen sulfate, then only penetration is observed on carbon steel. Very interesting observation here. You see all the lines is touching the y-axis, extend. However, for carbon steel, this one, you see the flat line here. The data only observed at this value, somewhere here. Then only the penetration is observed. Very special data here. So this is the explanation. So for carbon steel line, this one, for carbon steel line, this one, all right. So it stopped for lower concentration of hydrogen sulfate because FeS, right? Ferric ferric sulfate is not stable, and the steel does not corrode in such environment. So meaning if you expand this point down, you get one value. So those that below this one, so if you have very low hydrogen sulfate, carbon steels, it win over all the element over here. Because one reason in carbon steel inside there you have, it will form FeS. If you expose the metals to hydrogen sulfate S2S environment, it will form these products on carbon steels, FeS. But however, you know that when you don't have a stable products, you're not going to do anything on the subject itself. So steel does not corrode in the environment hydrogen sulfate. Yeah? Is observed under certain percentage. Okay. So you increase temperature. This is another graph. It shows you the temperature versus the penetration. I tried to find out from the textbook what is this axis. Graph should show you what is this axis, but I can't find the axis label here. But I assume it is a penetration value here, right? I don't have the unit, but this is the graph that I can find to explain about sulfidation. So here is a temperature with the rate of penetration. Okay, so if you increase temperature, you see the line here also increase, right? And what is the difference between these three lines is the concentration of the hydrogen sulfate. So if you increase, for example, this is the first test, your first experiment, you use 1 ppm of, what is ppm? 1 part per million. 1 part per million means you imagine you have 1 boxes of atoms, 1 million atom inside the box, and you put in one atoms of hydrogen sulfate inside the box, and then you mix around. So what happened to the environment, to the sample? So 1 ppm, 1 part per million of hydrogen sulfate, you show this line. And what happened if you increase to 10? It will increase further. If you increase to 100 ppm, it increase further. So as you can see here, what is this line? Okay. So if you increase the concentration from 1 to 100, okay, so by a factor of 10 may be needed to double the sulfidication rate. So what does this statement mean? It means you see the line here. If you look at only 1 ppm, right? Only 1 ppm. For example, this point and this point, it's almost double if you increase the temperature a little bit. From maybe here is 400, about 400 to 500 maybe. You increase the 100 degrees C of your temperature, your rate already doubled already, right? Almost doubled already. But if you increase the concentration to 10%, 10 times, or even 100 times, you see it's a bit slower compared to temperature. Means temperature still a very important parameter to watch. So temperature still dominate the penetration rates. Although concentration of the sulfur here, or hydrogen sulfate here, is increasing by 10 times or even 100 times. Okay, so this graph show you the importance of the effect of high temperature or temperature factor. Okay, so this one are the statements there. So I just draw 2 lines just to make comparison. Yeah. Okay, so this chart tell you that if you want to control the penetration, there are two factors. One is concentration, one is temperature. So if you choose between concentration and temperature, temperature have a stronger influence compared to concentration if you use this graph. Okay, so this graph just tell you there are two factors. One is temperature, one is concentration of the hydrogen sulfate. So both also contribute to penetration or contribute to corrosion rates, but temperature have a stronger influence compared to concentration if you refer to this graph. Okay. This is, okay, once we talk about the concentration and temperature on sulfidation, next we talk about chromium. Chromium content, what happened to sulfidation? Huh? So what is this graph will tell you? You see the temperature and the penetration rate here, and you have a loss of material here. So if you're interested, you can go and find out what is all these names, what is all this material content. But basically, it tell you those material with a higher chromium content, they can slow down the sulfidation corrosion. Okay, so this is another graph. Huh? So for example, alloy 304, or another name for 304 is S30400. Same thing, but different name, different standard here, but same material. Okay, alloy 304 or S30400. What does that stand for? Inside there, they have 80% chromium and nickel. 18% chromium and 8% nickel. So this one, this one is fall under authentic standard steels, and very common grade that used in the wire industry. So I have to highlight this one because this will be the most common seen material outside there. You as an engineer later, you will see this material almost in most of the industry place. All right, because alloy 304 is the most common material used in the wire industry, and you use wire everywhere, right? Okay. And this is another statement for the material. Another one is that 9 chromium 1 MO. This one is this line. This line here, 9 chromium 1 MO. So this one is a steel, as a martensitic steel, contain 9% of chromium, 1% of MO. And where do you find this 9 chromium 1 MO steels? They are used in hardened and tempered condition. Means this one you use this material for if you need a very high impact application, right? Those that you need to for example drill bit and all this, then you need they will find this percentage, these metals or this ingredient inside the tools there. So you can compare this one, 9 Cr1MO with this line. And where is this aluminium 304? Aluminium 304 with this line. S304. So this one have 80% chromium. This one CRMO, 9 CRMO is 9%. So you can see 9% this line. This line is 80%, almost double the chromium. You can see the line compared to these two lines. This line and this line, the penetration actually dropped quite significantly. The large distance here at the same temperature, if you measure at same temperature, you pick 2 points, this one and this one, actually the differences is quite huge, right? So both give you one penetration value, so quite huge. Yeah? So this slide shows you that if you increase the chromium, it's going to slow down the sulfidation. This is the graph that show you that if you want to stop or resist sulfidation, then you use chromium. You add chromium. Okay. This one, another one, just to explain what is alloy 410, or another code for 140, use the UNS system S4100. So this one is this line. This one consists of 12%. 12% chromium. So you can see this one is 9%, this is 12%. So 9%, 12% also got different one. Okay. So if you increase the chromium percentage, you're going to drop a little bit, although this one is 9, this is 12. So you still see the small differences in their penetration value. It means the corrosion value, right? Okay. Now this is more on the material selection for high temperature corrosion operation. If you have a high temperature corrosion and you need to choose between oxidation and sulfidation, okay, oxidation will be more important than sulfidation. If you have oxidation and sulfidation, the process will choose oxidation first because it dominates the high temperature corrosion domain. Okay, oxidation will happen more frequent compared to sulfidation. Okay, so if your devices need to work in the oxidation process, then it is recommended, this is the solution. If your process is more exposed to oxidation, although there is a sulfidation happen in the process, so in your operation you have oxidation and sulfidation, so it's recommended to use nickel and chromium alloy. High nickel and high chromium alloy if you have oxidation and sulfidation. Oxidation a bit higher in the operation, sulfidation still happen. If you have this kind of operation, oxidation is dominate the corrosion process, you use high nickel, high chromium solution, or high nickel, high chromium alloy. Okay. Example of high nickel, high chromium is in this red box. Okay, important is this concept, yeah. So the name you can find out, right? This is another example. So if sulfidation dominate, meaning in your operation, in your high temperature operation, sulfidation is higher compared to other corrosion methods. Sulfidation dominates means is the most high frequent happen. Sulfidation happen. Then the solution is low nickel. You see there's a difference. Low nickel, high ion means high Fe element, and high chromium alloy. So there's a difference, yeah. If you're working in a high temperature corrosion environment, you have oxidation problem and sulfidation problems. If these two problems exist in the operation, oxidation dominates kind of environment, you use high nickel, high chromium. However, if you have an opposite environment, you have sulfidation dominates, even there is oxidation happen, what you do, you reduce the nickel, you use low nickel, high ion, high chromium. Okay, for the material. This is the differences of choosing material. Huh? Okay. Okay, so this is another example. If you have a solidification condition, so this is explanation. Yeah. So solvidation of high nickel alloy, it can be happen very fast, and it can yield very high corrosion rates, 25 over year, if the temperature more than 630 degrees C. Just take note on that. Yeah. So high nickel is good. However, this is the weak point of high nickel alloy. So if high nickel alloy is used in the solidfication environment, the corrosion will happen very fast, and corrosion will also very fast. This one we have one value here, but this one you don't need to memorize. You only need to know when you have a high nickel alloys exposed to sulfidation, what happened? All right, the sulfidation corrosion will happen very rapid. Only one condition: the temperature have to control. The temperature, if it's acid 630 degrees C, the sulfidation going to happen very rapidly. It's not good. Meaning, this statement meaning, if you want to use high nickel alloy, control your temperature. If your temperature lower than 600, you still okay, still consider okay. If your temperature more than 600 degrees C or 630 degrees C, high nickel alloys will give you some headache, where sulfidication will happen very rapidly and it will destroy your devices. Yeah. So again, temperature you need to control if you have a high nickel alloy under sulfidation process. Yeah. Okay. Why? Because if you increase the temperature more than 600 Celsius, you might melt some of the corrosion products. Okay, you might melt some of the corrosion products, maybe the nickel oxide or nickel sulfate. So when you melt away all these oxide, all these products, meaning there is no more protection already. If you melt already these products, means you're not able to stop the corrosion, right? So again, this is just a highlight of this statement. Just remember, high nickel alloy is good for sulfidication, but you have to control the temperature. You have to control the temperature. Do not exceed 600 degrees C or 630 degrees C. Okay. Why? Because after 600 degrees C, there's a potential of melting the nickel and nickel sulfate. Okay, so this is the reason why we need to stress, if you work with the high nickel alloy, you need to control your temperature. Okay.
Sorry, sir. It's already 10:03, sir.
Okay. Yep. Okay. We stop here. All right, we stop here and we continue. We have class. We have class tomorrow. Yeah. We have class. Correct. Yeah, we have class tomorrow. Yeah. So see you guys tomorrow. 4:30 to 6:30. Okay. Let me stop the recording.